Okay, otherwise, I mean, there is a watch over there. That's fine. Okay. So, okay. So, so what I want to explain, as I said, is coming from mathematics, and I will propose an attempt, if you want, to understand the emergence of time. And this emergence would come from a fundamental notion, which is the variability. So I will first discuss variability. And I will first discuss, in fact, the notion of what is a real variable. So I guess, you know, if I would give you a piece of paper and ask you to give me a definition of real variable, I would get many times the following answer, that a real variable is in fact given by set X and the map F from the set X to the real line. Okay, and many people would be happy with this model of what is a real variable. But if you think a little bit about it, you realize that it's not such a good model. And the reason why it's not such a good model is that the discrete cannot coexist with the continuum. In other words, what I am saying is that if we take this formalism for a real variable, and if there is a continuous variable, then it's pretty obvious that if there exists a continuous variable, then the cardinality of the set X has to be a continuum. Okay, and if the cardinality of the set X is a continuum, then it means that any other variable on the same set X, so if I take another variable X goes to R, then if that variable G happen to be discrete, namely take only a countable set of values, then some of these values would have to have infinite multiplicity, and not only countable infinite multiplicity, but in fact uncountable infinite multiplicity. So this means that this formalism, as good as it looks at first sight, is in fact excluding the coexistence of continuous variables with discrete variables. So at first this looks very bothering, but it turns out that this problem has a beautiful solution, and that this solution is given by the quantum formalism as written by von Neumann. Okay, because when you take the formalism of quantum mechanics, I mean the one as written by von Neumann, then you find out immediately that a real variable shouldn't be thought of as a map from a set X to the real line, but it should be thought of as a self-adjoint operator. In Hilbert space, of course, in Hilbert space. I mean, when I say in Hilbert space, we all know that there is only one Hilbert space. And it is precisely this fact, the fact that there is only one Hilbert space, which makes a coexistence possible. Because, for instance, we can take the Hilbert space of L2 functions on the interval 0, 1, in which we have the obvious variable x, which is a continuous variable. But this Hilbert space is the same as the Hilbert space little L2 of the integers. And in that Hilbert space, we have the variable n, which is a discrete variable. So what we see, first of all, is that the Hilbert space formalism, the formalism of quantum mechanics, actually supports entirely the good notion of real variable because, for instance, the set of values of a variable is a spectrum of the corresponding operator. The number of times a value is reached is a spectral multiplicity, which is an integer. And moreover, now we have an enormous plus, which is that continuous variables coexist with discrete variables. There is only one nuance, which happens immediately, and that nuance is that a continuous variable cannot commute with a discrete variable. They cannot commute because if they would commute, there would exist a common x for both of them, and this is impossible. Okay, so the proof is one line, that they cannot commute. And so what we find out then, we find out that if one is led, if one simply lets oneself to be, led by this fact, one discovers the following. One discovers that, so I will not show you too many slides. I will go directly to the slide which interests me. And this is a quantum formalism, okay? And the fact that the discrete and continuous can actually coexist. And now I want to show you, a statement which I found when I was going to the Euler Institute for an anniversary of Euler. And there was a booklet which was distributed. And I was quite amazed to find a statement by Newton. When Newton was defining infinitesimals, he was not like Leibniz trying to define an infinitesimal as a quantity which is infinitesimal. He was defining an infinitesimal as a variable. And he was defining an infinitesimal variable. So what Newton was saying, first of all, he was saying in a certain problem, a variable is a quantity that takes an infinite number of values which are quite determined by this problem and are arranged in a definite order. And then he was saying a variable is called infinitesimal if among its particular values one can be found such that this value itself and all following it are smaller in absolute values than an arbitrary given number. Now, you have to reflect a little bit. Of course, this phrase looks a little bit like obscure. But when you think about it and you translate it in terms of the formalism of quantum mechanics, then you find exactly the definition of compact operators. So that if you want Newton infinitesimals, the Newton infinitesimals, they become compact operators. And I mean, if you know analysis, you know that compact operators share exactly the naive properties of infinitesimals. They form an ideal among operators and so on. Moreover, they have an order. Namely, for instance, an infinitesimal has order 1 if its eigenvalues are like 1 over n. Or the characteristic values, nth 1 is like 1 over n. And it has order alpha if it's behaving like 1 over n to the power alpha. And so you find out that these orders combine in the correct way, that if you multiply an infinitesimal of order alpha with another one of order beta, you get something of order alpha plus beta. And then you wonder, what about the integration? And it turns out that there is a universal integral, which is defined on these infinitesimals. And that was found in the 60s by Dixmier. And so this is the Dixmier trace. And so this integral, I mean, one has to have some convergence so that it exists, but the integral of an infinitesimal of order 1, it will be essentially, if you want, the coefficient of log lambda when you take the trace of t, in the trace of t, but you truncate the trace at lambda. So it's the coefficient of the logarithmic divergency. And it turns out that if you think carefully and all that, you'll find out that all the integrals we know can actually be written in that way. But now there is a meaning for both the integration symbol and the infinitesimal. They are separated. Normally, when you write down an integral, you have a meaning for the package, for integral of f of x dx. But here you have a meaning for the integral, and you have a meaning for dx. Okay. So I don't know where I wrote that in the slides. Yeah, so these are the infinitesimals, exactly. And now, you see, what I want to think about is the following. So first of all, we have this notion. Okay, so it is the notion of compact operator, and there is this filtration by order, and so on and so forth. And there is this dictionary, which I don't want to evolve on, but which is quite important, and which allows you to go further in the calculus than one normally goes, where at the end you have the line element, but you have the integral, you have infinitesimals, and so on and so forth. What I am interested in is not that. What I am interested in from the start is the notion of variability. Now, from what I said, you see, the notion of variability sort of leads you to the quantum formalism. The mathematical notion of variability leads you to the quantum formalism. And if I think about the lecture of Thibault or the lecture of Slava, then we have this Everett point of view and all that. And there is something which I want to propose, which is a philosophical idea. And the philosophical idea which I want to propose is simple, is that, you see, I remember when I was in high school, not in high school, in preparatory school for école normale. My teacher once asked me to go to the blackboard, and instead of asking me to solve an equation, my teacher did this. Okay, so I was doing this. And then he asked me, what is the variable? Okay, so I reflected, and after a while I told him, it's time. Okay, so, and this was the answer that he was expecting. Okay, now the topic of my talk will be the following. The topic of my talk is that I believe that we are all used, because of our constitution and so on, to attribute all the variability to the passing of time. I mean, this is, many equations in physics are written d by dt of something equals something else. So we are used to attribute variability to the passing of time. The thesis which I propose and which I will try to back by mathematical results is the following. I believe that the true variability is quantum, and that the true variability is exactly the fact that when you take a quantum observable, it doesn't have a single value, but it has many possible values which are given by the spectrum of the operator. Once you have found this, okay, plus the fact that discrete variables cannot coexist with continuous variables without the quantum formalism, then I will explain how can the times that we know emerge from these considerations. And in a very strange manner, it will be related to the last talk, to the end of the last talk. Okay, but I want to explain this idea in the best possible way. I have never tried. I know it's difficult, and it's difficult because in my mind it's backed up by an intuition, okay, which comes from many years of work, and this is the most difficult thing to transmit. Okay, so I will try. And the way I will try will be the following. So the idea then is that we start from this variability. So as I said, at the philosophical level, there is something quite satisfactory in the variability of the quantum mechanical observables. So as I said, you know, when you are pressed in the external world, you think about the passing of time, but I want to propose something different. So I want to propose that whenever we make, whenever we look at some phenomenon in which there is a reduction of the wave packet, in fact, we are wrong to try to write things in time. Because of our minds, which are logical, we are always trying to reconstitute a logical past, okay? Just because we want to feel happy about it. But what I am saying is that things might be different, and that there could be a fundamentally quantum variability. And what I want to explain now is a mathematical formalism that allows you from this variability to recover the time. Okay, so that's what I want to explain. Okay. All right, so I mean, one has to be very patient and try to explain as carefully as possible because it's a delicate, very delicate point. Okay, so the question then is the following. How on earth, if you have this variability, which is coming from the quantum, okay, can time, as we know it, somehow emerge? Okay, and that's related to emergent geometry, and that's, as we shall see, the ingredients will be the same. So now I am going to show you a picture. This picture probably will relax you a little bit. Okay, because what I believe is that the answer will come from somebody which is here. Okay, namely, okay, namely, what I will explain is that the work of von Neumann, suitably, of course, implemented and, of course, very much ameliorated, but it is his thinking which I think will be the potential explanation. And why? Why? Because what was von Neumann investigating with Murray in the 40s and in the 50s, he was investigating, and his motivation was from quantum mechanics. He was investigating the formalism of quantum mechanics that he had put up. But then there was a question, and the question was, what does it mean to have a subsystem. What does it mean, if you want, that somehow the Hilbert space in which you work is a Hilbert space in which you have kind of partial knowledge of things, because the system is a composite system, and there is a part of the system you know, and there is a part of the system that you absolutely ignore. So what von Neumann tried to understand was factorizations, and by this, of course, the first idea is that the Hilbert space will split as a tensor product of two Hilbert spaces, and that somehow, because you don't care about the Hilbert space, you only care about observable or operators, you will consider, and this is what von Neumann did, you will consider those operators which are of the form T1 tensor 1, and of course there is a reciprocal, which is the operators of the form 1 tensor T2. And von Neumann explicitly wrote in the paper, so this we can now look because this is an important thing. So what von Neumann was writing, he had set up the problem of factorizations, and he said another interpretation of this problem of factorization is suggested by quantum mechanics. The operator in the full Hilbert space, H, corresponds there to all observable quantities which occur in our mechanical system. But then, so this algebra B corresponds to the totality of all operators. But now, if sigma, this system, is decomposed into two parts, sigma 1 and sigma 2, and if we denote the set of operators which correspond to observable situated entirely in sigma 1 or in sigma 2, then he wrote down the properties of these algebras of operators which belong either to sigma 1 or to sigma 2. And then he continued with Murray, he continued to investigate these, which he called factorizations. So, I mean, we don't have to know much. You see, I mean, normally when you read about these things, you read that you have a weakly closed star algebra of operators. I mean, okay, so you don't know what is a weak topology, and you stop reading, okay? But the problem is extremely profound and simple, as formulated by von Neumann. It's really the problem of factorizations, okay, of Hilbert space, or of systems, if you want, of quantum systems, okay? And what von Neumann then found by investigating for several years with Murray, what he found is that thus our problem of solving this factorization corresponds to the quantum mechanical problem of dividing a system into two subsystems. And then he said, at first, you know, the interpretation suggests, of course, strongly that it should be possible to describe the Hilbert space as a space of functions of two variables, f of x and y, okay, which are square integrable, and where the sigma 1 would correspond to things acting only on the coordinate x, while the sigma 2 would correspond to things acting only on the coordinate y. Okay, so that was the first idea. Okay, but the marvelous thing is that this wasn't true. And what von Neumann writes is that the fact that the surmise of paragraph 2.2, namely this splitting, this very simple splitting, is not true, is therefore the most remarkable, particularly so, because certain features of the exceptional rings M seem to make them even better suited for quantum mechanical purposes than the customary B, namely that the full system. And what I am going to explain to you in great detail and with great patience is that this is how time can emerge, namely from such a factorization. Okay? What von Neumann found is that, in fact, you have three types of factorizations. So in his work, what he had found is that you have the first type, of course, namely that the Hilbert space does split into a tensor product of two Hilbert spaces. This is what is called type 1. And at first, you would not expect any other possibility. Okay? Then, moreover, he found a second case. And this second case, actually, I mean, this is I remember when I was in École Normale, I once was going around in the library, and I was looking at this paper of von Neumann where he found these continuous dimensions, and there I was absolutely amazed, if you want, because, of course, when people found something like that for the first time, they write about it in a special manner. And he wrote about it in a very special manner, because what he had found is that the case 2, what he had called the case 2, in that case, when you try to classify the subspaces, which would correspond to subspace of Hilbert space if you had an ordinary factorization, then what von Neumann found is that when you classify them, they are not like space is classified by an integral dimension, like you have in ordinary Hilbert space. They are spaces which are classified by a real dimension. And that real dimension can either be in a bounded interval, like 0, 1, or it can also be in an infinite interval, which is 0 infinity. And that distinguishes between what are called type 2-1, when the dimension is finite, and type 2 infinity, when it is in the second case. Okay. And this was the situation for a very long time. Type 3 was all that remains. Okay? And now some physics idea came in, and the work of Tomita, of course, and the KMS condition in particular. And so, I mean, the KMS condition, if you don't know what is the KMS condition, and if you look at it like this, you will never understand what it means. But there is a simple way to think about it. First of all, you know, what you want to do is you want to be able to switch phi of, you want to compare phi of xy, okay, with phi of yx. Now, in the case of type 2 factors, you do have a trace, so you have some state which satisfies that phi of xy is equal to phi of yx for any x, but not in general. And what Tomita was able to construct, if you want, was, so there is this theorem of, at first Tomita, but then Tomita-Takesaki, if you want, which tells you that if you take a von Neumann algebra, okay, so in particular a factor, and if you take a faithful normal state on M, then there exists a unique way of switching xy with yx by, at the price, if you want, of replacing 1 by sigma I phi of x, for instance. Then you can switch the two sides. I mean, the previous, the KMS condition, you can think of it just for the value I. It's enough. It tells you that by switching x and y, in fact, you can think of this as being essentially, formally, it's phi x, phi inverse. Okay, so essentially what you do, you think of phi as being something which has homogeneity degree 1. So when you take phi x, phi inverse, it has the same degree of homogeneity as x, and it belongs to the algebra. So that's the theorem. That was done in 1967. And we are still very far from the interesting point. And yes?
Be sure I understand the translation of the state.
Yes.
So you take any state?
Any faithful normal state, okay? Faithful means exactly what you were written, that an operator applied to the vector is not vanishing, okay?
And then there is
always yes, okay. Okay, yes. But of course it depends on the state, as here, okay? Now, what I proved in 1972, I was doing my thesis under Dixmier, what I proved is that, in fact, this evolution can be defined canonically without depending on the state. Namely, what I proved is the following, is that if you change the state, you will change the evolution only by trivial automorphisms, which are always there when you are non-commutative algebra, namely the inner automorphisms. Okay? So in fact, what happens then is something which is really mind-blowing, and what it tells you is that if you have a factorization of the Hilbert space, which happens to be of type 3, okay, not at all of the trivial type, then there exists a completely canonical time evolution, okay, namely a one-parameter group, unique modulo inner automorphisms, which go into this out M, okay? And to give you some intuitive feeling about it, you have to understand, first of all, that these factorization of type 3 are intimately related to systems with infinitely many degrees of freedom. Okay? So essentially, if you want to get a mental picture, you have to imagine that a factorization of type 3 is like this. You take a factorization of 4x4 matrices by 2x2 matrices. Okay? But there you take a state. Okay? And now what you do, you repeat this. So it's like repeating this quantum system many times. So you tensor it by itself many, many, many times. Okay? But to get to the limit, you have to know with respect to which state you are taking the limit. And so you fix a state on the first factorization. If that state happens not to be a trace, you will get something of type 3. Okay? And the amazing fact is the following, is that now you would think that, you know, the corresponding time evolution will depend on the state and all that. No, because what will happen is that when you change a state, you only change locally. You only change it locally. You cannot change it at infinity. At infinity, it has to remain the same. And because it remains the same at infinity, it means that the new time evolution will not differ from the previous, but only by something very local, which is the inner automorphisms. Okay? Now, of course, I mean, I didn't find this by accident. I found this after many months of computations because I had defined some invariant which was a period set of a factor, and I wanted to compute it. And once I found this result, it could be computed in an incredibly simple manner because it's just the kernel of this map. So in other words, these factors can have periods. They have periods. They have, there is a certain subgroup of the real numbers where they don't move, okay? And these periods, in fact, I proved that it could be many, many subgroups, not necessarily discrete in R. So already with infinite tensor product factors, this proved to be, okay. This proved to be, if you want, a very computable invariant. And then, sorry?
Non-continuous.
No, sorry? Well, of course, because the quotient it's a quotient by a group which can be very dense, okay? So now this led me to the classification of factors and to the reduction from type 3 to type 2. So immediately, if you want, it gave several invariants. So the first invariant that it gave was what is called a module of a factor. And I mean, this module is closed. For that one, it's a closed subgroup. So this is essentially the spectrum. And so this module is a closed subgroup of R plus star. And then it was splitting the factors by further classification in the type 3 case, which is the case 3 lambda, if you want, where this lambda is actually an element of 0, 1, of the interval 0, 1. And so this lambda belongs to the interval 0, 1. And what I proved, this was in June of 1972, what I proved is that factors of type 3 lambda for lambda different from 1 are reconstructed from a factor of type 2, from a fundamental algebra of type 2, and a single automorphism. Okay. Then after I did that, but long time after, Takezaki proved that the same was holding in the case 3-1, but then you had to replace a single automorphism by a one-parameter group. Okay? So that was a reduction from type 3 to type 2. But what remains, if you want, what remains is this completely mind-blowing fact, if you want, that somehow the factorization, which is not of the simple kind 1, which is not of the simple kind 2, it generates its own time evolution. So the operators will rotate with time in a completely canonical manner. And moreover, when you look back at the KMS condition, you find, of course, that the KMS condition is fulfilled by the Boltzmann state, which is given by trace of exponential minus beta h when you take the Heisenberg evolution of observables. Okay? So then there is something which I try to convey. Okay? And my feeling is the following. My feeling is that time, the passing of time, could very well come from the fact that we are unable to know all observables in the quantum mechanics. So I am referring, for instance, to the talk of Thibault when he was talking about the formalism of Everett, where you have a single Hilbert space and you try to look at the whole universe. The idea there would be the following, that we are unable to control all the observables of the universe. We are only able to control a small part of them, which is a factorization of this kind. And because of our lack of knowledge of the full observables, we have the feeling that time is passing. That's the idea which I want to convey. Okay? It's a rather brave idea in the sense that what I am saying is that it's our lack of knowledge, it's our lack of controlling the full algebra of observables which is actually generating time. And what I propose to do when we talk, about all these entangled state, all these experiments in quantum mechanics and all that, I want to try that instead of thinking in the usual manner where we write everything as an evolution, for instance, if we take an entangled state with 2 in the EPR paradox or something like that, and when we say, okay, we make measurement on this, then there is a reduction of the wave packet. But okay, what does this mean? At what time and all that? This confuses me totally. And I would much rather have a theory in which time is emergent, and somehow, if you want, it's a corollary of our lack of knowledge. Yes?
But isn't this very similar to the idea that people pursue in canonical quantum gravity when you write the Wheeler-DeWitt equation? There's no time.
Of course, I am coming to that. I am coming to that because, you know, for many years, of course, after doing my thesis, I was fascinated by this idea. And I was fascinated by the possibility that it could have a link with physics. But wait, I have not finished. But I was always disappointed, because even in quantum field theory, even in the case of the Rindler wedge and all that, I was always disappointed. It never convinced me at all. Okay, it never convinced me. So quantum field theory was not good. And then it turned out that in 1994, so quite a long time ago, in 1994, I was visiting the Newton Institute because I wanted to learn about gravity. So I was there. There was, you know, a whole program on gravity. So okay, they invited me. I was lucky. And then one day, there was a conference which was announced. And the title of the conference was, "We know what quantum space-time is." Okay. And it was by Carlo. Carlo is a very good friend. Okay. So it was by Carlo Rovelli. And that was the title of the conference. And of course, when I saw this title of the conference, I went to the conference, but my gun was not even under the table, it was on the table. So, okay, I attended the conference, and okay. And so we had a heated discussion. And so after that, okay, I began to discuss with Carlo. And we were having tea together, and the more I was talking with him, the more I saw that he had thought very deeply about these problems. So, I mean, I kept talking with him until the dinner. There was a dinner organized in the Newton Institute. So at dinner, we were sitting next to each other. And at some point in the dinner, I dared to tell him about what I told you now. So I dared to tell him, you know, there is this time evolution. And then Carlo left. So he was sitting next to me, okay, and he left. So I said, okay, I must have been rude with him for some reason, which I don't know. So, okay. And 5 minutes later, he came back, and he showed me 2 papers which he had written before. It was not, you know, like, okay, you know. So he showed me 2 papers which he had written before, and so what he had done, I will show you the papers because otherwise you won't believe me. But so what he had found, and this is amazing. I find, you know, that for purely philosophical reasons, which are exactly what you were saying about thermodynamics in general relativity, because the Wheeler-DeWitt equation is in fact a constraint of the system. So I mean, it's h equals 0. So there is, because of reparametrization invariance, essentially.
No, but what I mean is that the way they want to get time operationally out of this is precisely to split.
Okay, fine. Oh, very good. Okay, that I did not understand. So, but let me tell you what Carlo had in mind. So what Carlo had in mind was the following. He had in mind that because of this vanishing, there would be no natural Hamiltonian and so on. And then he had thought about it. And for pure philosophical reasons, he had found that the correct way was not from the sigma t, as physicists do normally, from the time evolution to the state, like a Gibbs state and all that. But he had shown for purely philosophical reasons that from the state one should go to sigma t. Okay. Now, okay. So he had written the equation, and this is his paper, Statistical Mechanics of Gravity and the Thermodynamical Origin of Time. And okay, I mean, I know that there are lots of things to say about it. I am not a physicist. I am not going to analyze this in great detail. But I was extremely struck by the fact that he had written the semi-classical form of the KMS equation. So if you want, what he had found is roughly, and I should add that G. Martel also, for a long period, advocated the following idea, which is that, I don't know if it corresponds to what you were saying, but I mean, G. Martel had advocated the idea that, after all, you know, the Lorentz invariance is broken by the relic of the thermal radiation from the Big Bang. So that somehow, you know, there is a relation between synchronization and thermodynamics. So this is what Carlo had written. Okay, so this is very easy to see that this is a KMS condition. Okay, that's very easy to see. And then, okay, from there, he had, you know, sort of tried to go in the reverse direction and explain this. But to me, I must say, I'm only convinced by the mathematics. And to me, this idea of von Neumann, this idea that you have a partial knowledge and that you have a factorization, plus the uniqueness, because many people don't know this uniqueness. I mean, of course, the Tomita-Takezaki theorem, but I mean, the uniqueness is extremely important. Why? Because it tells you that you don't have to choose a state. You don't have to choose a state. There will be this overall motion which will take place, okay, and which will, for each degree of freedom will be corresponding to the ordinary Gibbs state, but which will be independent of which state you choose, okay? Yes.
As it all sounds like people introduce a law of time using entropy, when second law of thermodynamics becomes tautology.
Yes.
In essence, because you are forgetting about knowledge, for instance, when you take trace density matrix.
Yes.
Then you define von Neumann.
Well, you see, I don't want to commit myself to that. I just want to say a mathematical fact. The mathematical facts are the following. They are that first, von Neumann was trying to understand what it meant to be a composite system, to a subsystem, okay? And out of this problem, which is a purely mathematical problem, formulated in Hilbert space, nothing else, okay? He found factors, okay? He classified factors, type 1, 2, 3, okay? Then came the time evolution, okay, and the uniqueness of the time evolution, which completely, if you want, allowed to classify factors, okay? So it cannot be, so the idea then is the following. The parameter T, you can say there is a parameter T, there is a one parameter group of things which happen, and so on. Of course, you can be blind, and I was blind for many years, okay? Now, on the other hand, if you take very seriously the idea that the origin of variability doesn't come from the passing of time, but comes simply from the formalism of quantum mechanics, from the Hilbert space. That's it, Then, I mean, it's absolutely vital that you can relate to ordinary time and time evolution as we know it. And what I am saying is that von Neumann and all this work provides a solution. And this solution, of course, depends on the fact that you have a subsystem. It depends on the factorization. If you had a trivial factorization, you would have nothing. You need a factorization which, in a sense, involves infinitely many degrees of freedom. A type 1 factorization is a factorization which involves only finitely many, doesn't involve infinitely many degrees of freedom. You need a factorization, and you need to understand intuitively. This is what is the most difficult to explain. You need to understand intuitively that this time evolution is sort of unavoidable. In other words, because it occurs infinitely at infinitely many components like this, you cannot suppress it. It's not inner. It's not an inner automorphism. You cannot suppress it. You see, it has the amazing property, for instance, that it is in the center of the group of outer automorphisms. So it tells you that any other automorphism of the algebra will commute with it. It's canonical. It doesn't depend on any choice. Okay.
Is there one case where you can describe this?
Yes, the simplest case, sure, the simplest case where you can describe this is infinite tensor product. So you take a system which is formed of independent systems that you repeat. So you take a single system, for instance, a spin system, okay, and you repeat it, okay, Ising model, for instance, okay, you repeat it infinitely many times. And then what you do is, okay, so you do this infinite tensor product with respect to a state which is not a trace, okay. Then what will happen is that this time evolution will be the ordinary Gibbs evolution in each of them, but on each of them, so it goes at infinity. So it is not inner. If it were inner, after some point it would cool down. It would be the identity. It's not, because it repeats everywhere. Okay. So the idea is the following. It's exactly what we are discussing in the talk of Slava. Repetition. It's repetition that actually will allow you to see this time evolution. If you didn't have repetition, you wouldn't see it, because you would be in the type 1 case. So it's the factorizations, which are infinite repetitions, which give you this time evolution. Otherwise, you wouldn't see it. Okay. So. Okay, I don't know if then one can go on and take the point of view that Thibault was explaining about Everett and then say, but what seems to be the case is that Hilbert space and Hilbert space operators know a lot more than what we think. We think that we have to add a lot of stuff with respect to Hilbert space knowledge and so on. But what I'm saying is this is not the case. And tomorrow I will explain, this is the work with Slava and Ali, I will explain that even for geometry itself, for emergent geometry, there is a very similar situation. So the idea there is to try, if you want, to take advantage of the setup provided by simple quantum mechanics, but of course complicated by the fact that we are dealing with subsystems, okay, and with factorizations. But it's very important to understand that I think there is a block, a mental block for many people, because when they talk about fundamental algebra, they say, oh, I think most of the people don't even know the distinction between a fundamental algebra and a system algebra. I mean, you know, they know that both of them are involutive algebra with some norm and so on, but they don't know the distinction between the two. And when you think about the work of von Neumann, it's quite different, because von Neumann had a very simple motivation, which was factorizations of Hilbert space. So what are called factors, they are the algebras which are abstractly isomorphic to one of the two, M1 or M2. And it's enough to know them to know the whole story. But I mean, if you want, the motivation has nothing to do with the weak topology, with the norm topology or anything like that. I mean, the motivation is much, much stronger. Yes?
But so if the universe was closed and finite,
yes,
time would not...
No, time would not flow, exactly. The suggestion, yes, it's an extremely strong, that's why this is the first time that I give this talk. You see, I mean, the idea is the following. The idea is that the passing of time is due to our partial knowledge, essentially. Because we don't have the full system, because we don't know the full system. Then how do we single out this subsystem? I don't know, okay. I mean, I am unable to know. But certainly, I would say that, you know, it will eventually, I mean, so what is the next question? Then the next question is rather obvious. The next question is, what are the observables? What are the observables for gravitation? Because what we were proposing with Carlo was that if we had a suitable algebra of observables for gravitation, then we should compute the corresponding flow, time evolution, and so on, and then we might get somewhere. Okay, and I mean, this would anticipate on my talk tomorrow, but what one finds, if you want, is again motivated by an extremely simple question, and I can ask this question here. I will not probably answer because of limitation in time, yes. But the question is remarkably simple. How can we say where we are? How can we transmit to aliens our address? Okay? And of course, this has to do a lot with what are the observables for gravitation. And okay, what I would say is that it's well known. But I have a mathematical contribution to say on that. So, I mean, it's well known by a little paper of Milnor that it's not enough to know the spectrum of operators, like Dirac or Laplacian and all that. This is well known. What is less known, because I wrote a paper about it, but as you were saying, you know, this paper was totally unnoticed. And I think I know why it was, well, one possible reason, because the new invariant, I called it the CKM invariant. Okay, so what I proved in this small paper, I proved that there is a complementary invariant to the spectrum of the Dirac operator, or the Laplacian. And this complementary invariant is simple to understand. It's the relative position of two algebras. So it's the relative position of the algebra of measurable functions on the manifold. Now, by a theorem of von Neumann, this doesn't depend on the manifold. So if you take two manifolds, you can take a sphere, a torus, whatever you want. They have the same algebra of measurable functions. Okay, that's and they act in the same way in Hilbert space. So that algebra in Hilbert space is well defined. And now this algebra has a relative position with respect to the algebra of functions of the Dirac operator. Okay, so there are these two algebras. Okay, if you know that relative position, then you have the additional invariant which gives you the geometry completely. And the reason why I called it the CKM invariant is that the Kabibo-Kobayashi-Maskawa invariant is exactly the same, in the sense that what you do is you take mass eigenstates for the upper quarks, and you use a weak isospin group to put the mass eigenstate of the lower quarks up. And then what you get are two algebras in the same Hilbert space. and you do exactly the same thing. So I usually illustrate this in the following way, that after, so you have this unitary CKM invariant of Riemannian manifolds, and I illustrate this usually by showing you the simplest example of the new invariant, which happens because after Milnor, of course, the counterexample to isospectrality was reduced very much. So these two things, for instance, are isospectral. These two things also. This is due to Chapman. But in order to show you the new invariant, it's better actually to show you two other examples. So this is shape 1. It's disconnected, but don't worry about that. Okay, so it's an isosceles triangle. Square isosceles triangle and a square, little square, and that's isospectral to this. So it's isospectral to a rectangle and a smaller isosceles triangle. Okay, I mean you can play with it. You can find the spectrum. You will see they have the same spectrum. Okay, but they don't have the same invariant, second invariant, and the reason why they have okay, so they have the same spectrum. I mean I don't want to insist on that. The reason why they don't have the same second invariant is the following, is that, in fact, when you look at this spectrum, you find 3 types of nodes, because you find integers plus 1/4, integer plus 1/2, and integers, okay, in the square of the spectrum. So there are 3 kinds of nodes, which are clearly distinguished. But when you look at the possible chords, and I will explain what is a chord, so this is like the piano, if you want, on which you can play in both cases, because there are 3 kinds of notes. But somehow I will call something a chord if there exists a point at which the corresponding eigenfunctions both don't vanish. Okay, so and there could be 3 or whatever. Okay, so and it turns out that the chord which is blue-red is not possible for shape 2, but it's possible for shape 1. And so in general, if you want the new invariant, what it tells you, it's intimately related to the idea of a point. And the point in that view, which is spectral, is given by correlations between the eigenvalues. So this is the idea. Okay, so that the points, in fact, because after all, if we want to say where we are, we not only have to give the space, the geometry, but we also have to specify at which point we are. And the way you specify here at which point you are is by giving a Hermitian matrix, which is the Hermitian matrix of scalar products of spinors at the point where we are. So you have eigenspinors, and you can look at the corresponding matrix. That will be exactly what you need to know the point. So I mean, okay, of course we know we have this. Okay, so I will finish here. I will actually finish here, and I will continue tomorrow on this spectral framework. But I mean, I always hesitated to give this talk because it's an intuitive idea. It's based on mathematics. I'm not saying that with Carlo we made the best use of this mathematical theorem. I mean, I'm not saying that, and I know, you know, that in physics you have to think a lot, you have to try to find counterexamples and so on. But I hope I conveyed the intuitive idea. The intuitive idea is that there are factorizations which are so with infinitely many degrees of freedom that they generate their own time. Okay, and this is by partial knowledge. Namely, if it was a full thing, nothing would happen. It's only because it's a partial thing that something happens. And of course, it's related to thermodynamics and temperature and all that. Okay, so I think I will.
Me? Yes.
Yeah. So let me return back to this question about closed intervals, which is supposed to expand and then contract. Then, according to your statement, principle you cannot introduce in such a way time that it would proceed all the way from the beginning to the end. What is the reason?
Okay. But let me answer your question. Yeah. You see, Carlo actually wrote 2 papers. Okay. I cannot say I'm very convinced by the second paper, but in the second paper, what he was doing, he was taking a Robertson-Walker model. Okay. And then he was computing this thermodynamical time, okay? And then what he found is that actually there is, if you want, you have a temperature which depends on time, like beta of t, so the flow lines are the same, but there is a rescaling by beta of t, okay? So, okay. Then if you want, the issue, Okay, I mean, I don't know how to answer your question, but when I read this paper, I was a little bit taken aback in the sense that he was putting by hand the thermodynamical state. And of course, you know, in some sense, I mean, one has to be very careful because in the von Neumann spirit, what is really important is that you have a fixed Hilbert space, and then you have a weakly closed algebra of operators. If you had only, like in the talk of Klaus, if you have only star algebra, and you use the state to make the completion and all that, then you are not in such a good situation because, you know, then if you change the state to another state, you will get another thing. So, I mean, it's very, very important that you stay within the framework of a single quantum. So, I think it fits with what Thibault was saying about Everett, namely that the model should be, you have a Hilbert space and you have okay.
You know, because a similar question was considered by Bryce David, in fact, because yes, you understand that this superspace approach, when you write these equations, there is no time.
Exactly.
Then you try to introduce some time. For instance, David was introducing some clocks from dust or whatsoever, so he was introducing some operators which were built from the other variables. So then there was so-called error of time.
Yes, okay.
On the other hand, okay, for the closed universe, wave function was somehow symmetric, okay, with respect to the bounds. But he found the following solution in terms of Everett interpretation. He said that before we are interpreting the whole thing, we take the whole wave function, decompose it in sub-component, then the whole picture looks symmetric, but you are getting universes where time in one universe goes in one direction, in the other universe you try.
Can I say something? You see, what is very important to know here is that the direction of time is specified. Because what happens is that, as I told you, for instance, you know, there is the periods and there are things like that. So the reason why it is specified is that when you write exponential minus beta h, you cannot change h to minus h because you need a state. Okay, so this is very important. And this is why you cannot reverse time. So, I mean, this looks like a triviality, but it's not. I mean, you know, so you cannot reverse time. So it's not true if you take a fundamental algebra that, for instance, the time evolution that I explained to you would be the same if you change t to minus t. If it were the same when you change t to minus t, then it would be trivial.
No, I say opposite things that you cannot change because actually entropy, by the way, in each branch is growing. But because you have many branches, then you can have. It was the same story because Hawking was making statements that in this closed universe, because of CPT invariance, when universe will reach maximum radius, the error of time will reverse, and then all broken glasses go back on the table. You see? But it was just wrong treatment, because the same thing actually was faced by the
I understand. I mean, you see, I mean, I cannot really discuss the physics. I mean, what I want is to transmit the mathematical fact. The mathematical fact is extremely striking, I think, you know, that, and it suggests a philosophical fact, which is not a physical fact, which is that the fundamental variability is quantum rather than the passing of time.
Yes.
So if I go back to the factorization problem,
Yes.
you started with a 1 started with, then there may be several factorizations.
Of course, yes.
And then there are different notions of time.
No, but I mean, because you have different algebras, of course. But if you give a factorization, there is only one notion of time.
Okay. Sure, yes. But how do you get this subsystem? I mean, physically, or how?
Well, okay, this is physics now. Okay, how in physics can you define the subsystem which corresponds to the passing of time? This I cannot answer, of course. I mean, you know, but I mean, if we take the point of view of Everett that, for instance, Thibault was explaining, then I would say that, okay, you have this state vector or something, and then you only have knowledge, or if you want, of certain algebra of observables, which is not the full algebra. You have only a partial knowledge. That is the idea. Yes.
No, I mean, if I start to make remarks, it's going to take an hour. But I think there are some, I believe there are some major misunderstandings in the story we heard about the time. You see, the time doesn't come from a single algebra, it comes from a funnel of algebras. that are embedded into one another.
Might be. I mean, okay.
If you have an equilibrium state, in fact, suppose there's perfect equilibrium, then Slava's quantum fluctuations never form structure. It's very important that you're not quite in equilibrium.
Okay, but I mean,
that's what makes the time flow.
No, but okay, I mean, but when I told you that it's unique up to inner automorphisms, it means exactly that you have this flexibility to change it locally. So you can be locally out of equilibrium.
Anyway, I mean, you know, I've made some proposals which we could discuss, but it would take more.
Yeah, but what was my point? It was to stress the mathematical fact. Not to stress the physical interpretation. I mean, it could be that for the physical interpretation you need a funnel of algebras or whatever. But, you know, I mean...
maybe T-time would
but
be...
But can you clarify, in your example of infinite tensor product, you say the state on each copy has to be, what, impure? You need any row?
Oh, yeah, sure, of course, yes. Yeah, sure, it is density, which is not pure. Yeah, exactly.
But if it is pure, you have nothing?
No, because you can have a pure density matrix which on the subalgebra in the factorization induces something which is not pure, of course.
No, but in your example of infinite tensor product, I need a row which is trace of square different.
No, I was thinking differently. I was thinking, So factor, for instance, 4x4 matrices as 2x2 times 2x2, okay? Now take a vector, pure, in 4-dimensional Hilbert space. Now, this vector can be such that the condition he was telling in his talk is true, namely that it's faithful for one algebra. Okay, and then what you do is you do the infinite tensor product of the 4-dimensional Hilbert space according to this vector. In that Hilbert space, you will have all the left algebras will act together, and all the right algebras will act together. And that will be a factorization, which in general is of type 3, unless the vector is a trace vector, which is extremely rare. I mean, there is only one.
So you look only at the factor.
Sorry?
So it's the factor which is, I mean...
Yeah, sure. So you take a trivial factorization of 4x4 equals 2x2 times 2x2, okay, and corresponding vector, and you just repeat it. You repeat the same. That's enough to get a type 3, to get the time evolution. And the time evolution will be the one you
But the time evolution is in the subparts?
In the subparts, of course, in the subparts. It's not on the full thing, it's in the subparts. Of course. Sure, of course. It's in the subparts. Sure.
One last question.
Yes.
If I understand your definition of time depends on the system you are studying.
Yeah.
So have you an idea of the correlation between the two different systems that are...
Well, okay, sure. Okay, that's a very good question. It can happen, of course, that the subsystem is invariant under the time evolution of the bigger system, in which case the restriction of that time evolution will be the right one. That can happen, and I suppose this is what you got in mind. Okay, this can happen, of course, but it's rare. It's very rare. I mean, in general, if you take, a sub-factor of something, it will not be the time evolution will not restrict at all, not at all. By the way, I should say, that of course this was the motivation why. Then, I spent many years studying non-commutative geometry. And why? Because these factorizations, the simplest geometric origin of this factorization of von Neumann is foliations. If you take foliation of a manifold, you get a factorization of von Neumann. And the simplest foliation, simplest. If you take, for instance, the O-cycle geodesic foliation on the sphere bundle of a Riemann surface, you get type 3-1. So you really get, the most exotic factorization of von Neumann.
Maybe we should postpone the discussion to tea. Thank the speaker.